So here's what an exponential function. We're looking at just 7-6 exponential functions. This lesson will be kind of like what we did with those absolute value functions. We're going to discover what they look like in general and where we might use them. But a function, remember a function is just a rule. And it's what a function is you give me a number to put in, and then I evaluate it somehow, and there's an output. So like a linear function was an equation that made a line. So you give me a number, I put it in, give me another number, we put them all together, we have a bunch of dots in a line. Well, this one is a function where the variable is an exponent. So this is pretty different. Okay, see how the variable is an exponent here? That's the y equals 2 to the x. So I think we could answer our little problem. Did you figure it out already? 28 days. How many pennies you have? Okay. So this is really the equation that we'd want to think about right here. This y equals 2 to the x. So like day one actually, what? Oh, go ahead. So we would start actually maybe with we start with days, yeah. So day two would, the equation would be a little different from this. We'd have to have that power be x minus 1. Power would have to be x minus 1, so that like day one, it would give you 1 penny. Because 2, so we could figure out how rich he would be if I paid him a penny a day, doubling the amount each day. The equation would look like this, 2 to the x minus 1. So here's xy table, day 1. I plug in 1 here. What's 2 to the 0 equal? 1, right? 2 to the 0 is 1, so that's 1 penny the first day. And then the second day, I would pay him, that's 2 minus 1, 2, that's 2 pennies. And then the third day, 4 pennies. Fourth day, 8 pennies. We're still just talking pennies here. But he gets to keep the penny, and even if I said, well, let's just let it accrue and see where we land on the 28th day, even the 28th day is quite a bit. But if you take the 28th day and add all the pennies I gave to him on all the previous days, he's really rich. But it goes like this, and we'll just extend this down a little bit. Let's just see, take it a little, until we get into the dollars, just so you get the idea here. 32 cents, we still haven't hit $1 yet, right? 7th day, we're now at 64 cents. 8th day, now stuff's going to start to happen here. It's going to start getting crazy. So you reach about the middle of the month, and you go, oh, this is interesting. 256, and then 10 would be $5.12. So on the 10th day, I'm paying him $5.12. The 11th day, paying him $10.24. I should have little points on those up there. At 12th day, it's $20.28. And then, of course, we're adding up all the previous days. 13th day, it's $40. So by the 13th day, he's already ahead of me, just giving him double what he had loaned to me. What's up? It would be 48, which makes this better. So this is $40.96. Okay. And then the math's getting too hard for me, but that's where exponential functions come in. I think the next one would be $80-something, $160. Yeah, you just plug in this equation up here, and that's what we're going to learn. See this equation right here? To find out how much I made on the 28th day, I just plug in 28 right here, 28 minus 1. It'll give you a number. Of course, that'll be in pennies. It just moved the decimal 2 places over, and you got it. So yeah, you plug in 28. What do you get when you plug in? Will the calculator handle that? Let's try it on mine to see what happens. So it's not. So if you go over here, let's just do this real quickly. So we type in on our
168,435,456. That's a big number.
Cool. You guys got to see this number. So it's 2, and then you hit your little. Remember this guy right here? 2 to the, and then in parentheses I put in 28 minus 1. 28 minus 1. So that's the power. Whoops. 28 minus 1, and then there it is in pennies on that day. So if you move the decimal 2 places to the left, it's this number right here. Just that one day. Just on the 28th day. But then I had told him he gets to keep like all the previous days amounts of money. So that'd be a lot. Even if I just said, oh, I'll just pay you, you know, keep track, and on the 28th day of February, this is how much you'll get. That's 1, 2, 3. So we're at like 1.3 million. So Ian was right. He'd be a millionaire. You know, even better than that if the next following month that I was paying back had a few more days in it, right? And then even better if he gets to keep all the money from each of the previous days. So yeah, it's a good business move for him. That's an exponential function. Back to here. Now look at the other exponential functions here. Here's another one. This is negative. Y equals negative 2 to the x. Notice that it's taken this red exponential function and flipped it over. It's called a reflection. Look at this 1/2 to the x. When you talk about shelf life of some kind of substance, it could be in the medicine field, and you think like medicine fields, you have some kind of medicine sitting on the shelf that has a shelf life. And what's happening? What's that? They call it the half-life. Yeah, and so what the half-life means is that after every certain amount of days, like maybe every 30 days, or it could be every 120 days, half of that substance is all that's left. So it's dissipating, you know, whatever's happening now. So that's what the graph of that medicine would look like. And so, you know, if you give somebody some medicine, it gets into their system, right? It's going to kind of have a maximum concentration, and it's eventually kind of go out. So you might have to do calculations where you're figuring out after how many days can they, or after how many hours maybe can they go ahead and drive again. They're finding it safe to be behind the wheel. They've taken some medicine, so they're not able to be behind the wheel of the car. Yeah, what's that? Basically, yeah. And so you have to figure out, okay, here's the graph of that. At what point are they below a certain level so that they can function correctly? And so that's exponential as well.
This is why it's useful. Real life situation.
What's that?
That's why it's useful.
It is super useful. Yeah, exponential growth and decay. All right. So a little bit of information, maybe more than you wanted, on exponential functions and their usefulness. So what we'll do is first we have to understand the difference between a linear one, which is kind of our, for Algebra 1, the linear function is like the building block. It's the first function you're introduced to. It's the building block of all the functions. And we need to know the difference between an exponential function and a linear function. So here's a table. It says, does the table or rule represent a linear or an exponential function? Do you guys remember what are we looking for on the y values as we go from here to here if it's linear?
Oh, if it goes up equal amounts.
Yeah, it has to go up equal amounts. I'm going to write that. Go up equal amounts, question mark. This is for a linear. So this is definitely not linear because it does not go up by equal amounts. At least by what we call a constant difference. So it does not go up by equal amounts. It does go up by equal, what we call multiples, believe it or not. And that's what separates out an exponential function. So we at least know that this table is not linear, right? And that's all we did last semester, is it linear or is it not linear? Definitely not linear, but we can take it a step further, and we can figure out if it's exponential or not by checking for constant ratio. So look for a constant ratio. So right here, the constant ratio can be found by doing the following. You take 3 and divide it by 1, and you'll get 3. And then you go to the next one, which is 9. Take 9 divided by 3, and you get 3 again. And if I take the next one, 27 divided by 9, look what I get. 3 again. And so the constant ratio exists. That means it is exponential. And so you're looking for a constant ratio between the next term and the previous term, next term, previous term, all the way throughout the whole table. Okay, so this one is, right next to it, exponential, because it goes up by a constant multiple of 3. Ratio of 3. Okay, so
that's it.
that's it. You're just telling me, is it linear or exponential? Since it's not linear, you could have just said it's exponential, but I'm telling you, I know it's exponential because it goes up by a constant ratio of 3. What about here? Y equals 3x. Is that linear or exponential?
Linear.
It's linear just because why?
Because it's a slope, so it's 3
Yeah.
over 1.
It has a slope of 3 over 1. It's in the form y equals mx plus b. You know that form. So it's linear. What about down here with the table?
That's exponential.
Ah, okay, good. I did not trick you. I thought maybe I'd trick you with that one. It is definitely not linear because from here to here, that's a difference of 1, difference of 2, difference of 4. But if you look at it a little more carefully,
It's ratio of 2.
8 divided by 4 is 2, 4 divided by 2 is 2, 2 divided by 1 is 2. So this one is also exponential. So exponential. It has a constant ratio of 2.
Couldn't the next one be both?
Well, where is the variable?
Above.
Now, when the variable is a power, variable is the power, then it is exponential. So that one is also
So
exponential.
if it has a power of x, it's exponential.
If there's any variable in the power on the base, it is exponential, yeah. If you were to make a table for it, let me ask you another question. You know what the constant ratio would be for that last equation here?
Which one?
This one right here.
Wouldn't that be anything?
Let's see. Here's how we could tell. Can we make a table for this? So if I plug in 1 for x, what's 7 to the first? 7. If I plug in 2 for x, what's 7 squared? 49. If I plug in 3.
That's like 130 something.
7 times 7 is 49. 49 times 7 more would be 280 and 63. What's 280 plus 63? 343. That's as far as we need to go. If I take 343 and divide it by 49, it will equal 7. If I take 49 and divide it by 7, it will equal 7. If I were to continue with that pattern, the constant ratio is 7. It is exponential, yeah. It has a constant ratio, and the constant ratio is the base. So if I were to go back here, could you tell me what the equation of this table is right here? Y equals
2x.
2 to the x, yeah.
Oh my god.
So if you plug in 0 right here, 2 to the 0 will be 1. 2 to the first is 2, 2 to the second is, and 2 to the third is 8. So at least that one's pretty easy to find the exponential equation. It's not always that easy. What? Just start there, yeah. That is pretty big, actually. There's a whole unit in Algebra 2 we talk about arithmetic and geometric sequences, and we could totally do that. It connects to that. So this is huge. These 2 words. What's that? Go up a little bit? Yeah. So we had exponential, exponential, exponential. The only one that was linear was the one that looked like it was in y equals mx plus b form. If you were to make a table for it, you'd find out that the y's go up by a constant difference, a constant number. Whereas the exponential ones go up by a constant ratio or a multiplier.
Is that it?
Yeah.
Oh.
I think there's more. We want to actually learn how to graph these a little bit. So we're just all we've talked about is how do you know, based on a table or an equation, whether it's exponential or not.
Oh, we have to do the -2 and 1, 0, 1, 2, 3.
Yeah, we're gonna plug in. Yeah, we're gonna plug in values. We're gonna get the range. We're gonna plot the points. Get what it looks like
Tomorrow.
today. And then we're gonna look at some word problems real life sorts of work on where you would model it with an exponential function.
Wait. Oh,
All right. So evaluating an exponential function. This is, we kind of already did this. So it says suppose 30 beetles are left alone in a bin. The population doubles each week. The function y equals 30 times 2 to the x gives the population after x weeks. How many beetles will there be after 56 days? A lot of beetles.
Wait, don't we have to keep
Yeah, so you'd go 30 times 2 to the 56. Oh, it doubles each week. So the function y equals gives the population after x weeks. So x represents weeks. So I wouldn't plug in 56. I think that'll overrun your calculator, actually. So 56 days equals how many weeks? 8 weeks. So I'm going to actually plug in, I got to be careful, 8 here for weeks. Okay, so just be aware of that's weeks. So maybe make a note of that. 56 days is 8 weeks, so good thing we read it carefully. And so we would do 30 times 2 to the 8th. You want to do the 2 to the 8th maybe first. If you're going to do it separately, do the 2 to the 8th first, because the rules of arithmetic, your order of operations, if you will, says exponents first. PEMDAS says exponents first, then do the multiplication. If you do 30 times 2 first, you're going to get 60 to the 8th, which is a completely different value than what you're getting. So 2 to the 8th times 30. What's 2 to the 8th equal?
2 to the 8th, 2 to the 9th. That's a really big number.
2 to the 6th is 64. 2 to the 7th is 128. 2 to the 8th would be then 256. So just be aware of that you need to do that 2 to the 8th separately. Actually, if you type it into your calculator in that order, it will know to do the 2 to the 8th first. And multiply by 2. Give you a what? Well, let's try it. So on your calculator, you would type in 30 times 2 to the 8th. And you got to make sure that it doesn't do the 30 times 2 first. So look like this. I think it should do it 256. Yeah, it did. So it's fine. It's the same as 30 times 256. So 7,680 beetles. So 7,680 beetles. You should get 256 and 2 to the 8, and then times 30.
Oh, that's a lot of beetles.
A lot of beetles. Uh-oh, rabbits. You get it? An initial population of 20 rabbits triples every 6 months. Yikes. The function y equals 20 times 3 to the x gives the population after x half-year periods. So these are half-year periods. So 6-month periods. So how many rabbits will there be in after 3 years? So 3 years equals 6 half-year periods. So we'd have y equals 20 times 3 to the 6th. So how many rabbits do we have? What is it? Did you get it? The actual number?
14,500.
14,580?
Wait, no, wait.
That's what
Wait, what do you do with the, oh, I did 20. I mean, I did 30, not 20.
Yeah, that's right.
It sounds about right.
Yeah, it's 14,580. Sorry, I did 30.
14,580, yeah. Lots of rabbits. So exponential functions model population growth, at least to a point. There's this point of when they state of equilibrium, in which they're going to run out of space and food, right? Things like that, and so they'll start to level off. There's a better equation that we derive and talk about in calculus, called the logistics equation. You can use the equation without knowing calculus, but we can derive it in calculus. It's kind of a neat equation. It's a better model than this. They're eventually going to level out. It's just they can't keep rising like that. And slow down.
They just keep getting food.
And space. Yeah. And no predators. Then theoretically they could keep getting right. Does everybody have that? What's that?
Don't we have to reduce the exponential?
Yeah, it's the equilibrium state is what we call it. But yeah, I mean, if they're in some given space, yes, they're eventually going to be that.
You see with all the ramps on this, we can go around.
Use a rabbit ladder to go back and forth. All right, so graphing an exponential function. So here's what you're going to do to graph it. You're going to do the -2, -1, 0, 1, 2 thing. You've got to know how to evaluate it using these first two rules of exponents. It goes back to the first section. Yeah?
What are you just plugging the number you want into the x?
Yep. So it'll look like this. For the first one, it would be 2 times 2 to the -2. And you can type it right into your calculator if you'd like. I could do this by hand. It's 2, and then you move the 2 squared to the bottom, which is 2 over 4. Remember, 2 to the -2, move it down,
which is 0.5.
Which is 0.5 or 1/2. Yeah.
Wait, why did you start off with -2?
Hmm?
Oh, because it's the x. Oh my god.
I'm plugging in the x values. On your calculator, you could type in 2 times 2 to the power of -2, and you'll get the same thing. So use your calculator if you want. But you know, with our understanding of the rules of exponents, we're able to do this by hand. Should be able to. And then you'll start to see a pattern here. 2 times 2 to the -1 ends up equaling 2 over 2, which is 1. What's 2 to the
4?
Oh, let's see. Let's see. This is
No, you're doing it right. So
2, 1/2.
0, 2. Wait, no, it should go 2, 4, 8.
It should go 0.5, 1, and then this should be, if it continues the pattern, it should be 2. It is. 2 to the 0 is 1, and then times 2. So 2 times 2 to the 0 would be 2 times 1, which is 2. So that's 2. And then if you plug in 1 here, because of this 2 out in front, it's got a little bit different pattern than our original equation we looked at. This would be 4, and then this would be 8. And so we need to take those and then plot those points. So we have -2, comma 1/2 would be right about here. -1, 1 would be about here. 0, 2, about here. 1, comma 4, about here. 2, comma 8, about here. And then you can connect it. Connect the dots. You should have a nice smooth curve. You could put arrows on the end. It doesn't actually touch the x-axis, but it gets really close to it. It's getting closer and closer and closer to it. It does not touch it. I don't care how big of a negative number you plug in for x, it will not equal 0. Be really close.
Okay. Watch. If you put pi in there, see what you put pi, would that reach the 0?
Go for it. Try it. You put what you'd want to do, based on this pattern here, is you'd want to keep going until you had a really big negative number.
Can you do -pi? Is that even
Try negative pi. Try it, but negative pi is not even going to be as close to 0 as like plugging in -100 or -1000, -1,000,000, but you still won't get 0. Your calculator will kick it over to scientific notation.
Yeah, it does.
But it won't be 0.
It's 10,000.
Yeah. All right. What about this one? If I plug in -2 here, it'd be 1/2 times 2 to the -2 power. You could plug this into your calculator if you'd like. You could do it by hand.
0.125.
You could go like this. It'd be 1/2 is the same as 0.5. I can't remember what it was. Times. It was 2 to the x, okay. So 0.5 times 2 to the negative 2. So you just type in 0.5 times 2 to the power of negative 2. And you get 0.125. Do you know what fraction that is? 0.125? You have to. It's a good guess. 3/4 would be 0.75. Yeah. Give it a guess.
Wait, can you see?
That'll be, oh, it's
1/8.
That's it. It is 1/8. Good. It's 1/8. So if you go back to here, we could totally do this by hand. This is 1/2 times 1 over 2 squared. Well, 2 squared is 4, so it's 1/2 times 1/4, which is 1/8. So, I mean, if you want to write it as 0.125, be my guess. 0.125 happens to be equal to 1/8. Do this by hand. If you plug in -1, we have 1/2 times 2 to the -1, which is 1/2 times 1/2. What's 1/2 times 1/2?
How do you write -2 1/8?
How do I get -2?
How do you graph that?
-2 1/8. You just do the very best you can. It's really close to the x-axis. So the next one will be 1/4. What do you think the next one's going to be if I continue that pattern? 1/8 with 1/2. And then if I double 1/2, yeah. Because this is going to be 1/2 times 2 to the first, which is 1. And then the next one will be 2. So, yeah, good question. How do I graph -2 1/8? You just do the very best you can. I place the dot really close or right just above the x-axis. And then at -1, I'm at 1/4, which is not much higher up. And then at 0, I'm at 1/2. So those first 3 dots are all below 1, but above the x-axis. You're just estimating where they're located. And then at 1, 1, and then 2, 2. That's it. So we looked at graphing exponential functions using a table, deciding if something is an exponential function based on the table, and then plugging in numbers to an exponential function. That's it. That's all there is to it. At least for today. There's more to it. But for us, for today, that's all we're doing.
Okay, so I learned how to graph exponents, right?
You learned how to, your summary would be, I learned how to graph exponential functions, yeah.